Welcome back to Honors Calculus. In this video, we're going to be looking at evaluating definite integrals. Now, we've already used some geometric techniques to calculate the value of a definite integral. We've also used the limit definition in order to do so. But now we have the powerful tools. Now we have the fundamental theorem of calculus and the idea of anti-differentiation. And so our goal here is to use those tools and find a way to relate those to doing work with definite integrals. So without further ado, let me get my head out of the way, and I'm going to start with a corollary to the fundamental theorem of calculus. And in fact, developmentally, this idea is what came first. And a lot of textbooks still use this version and call it the fundamental theorem of calculus. I don't, because it is a corollary. It builds on the other idea. But this is the way that the fundamental theorem is used. So we want an integral function little f, and we want an antiderivative so that f prime, big F prime, is equal to little f on the interval from a to b. Then, to evaluate the integral from a to b of little f of x dx, I claim that all we have to do is take capital F, evaluate at b, take capital F, evaluate at a, and subtract those two things. That is amazing. In order to find the area underneath a curve, all you need to do is figure out an antiderivative and evaluate it at the endpoints of the region. All you need to do, right? But first, let's take a look at a proof. The first thing I want to say is that for any x in the interval from a to b, the integral from a to b of f of x dx is equal to the integral from a to x of f of x dx plus the integral from x to b of f of x dx. That's just the properties of the endpoints of integration. And in fact, this is true even if we set those limits of integration to be something else. The next step we didn't really talk about in too much detail. I think I mentioned it in passing, but we didn't do anything with it. Had to do with negative area. If we think about the area underneath the x-axis as negative, it turned out that it was also useful to think about area as being negative if you looked at it going the wrong way. So instead of going from left to right and calling that a positive area, going from right to left, we're going to call that a negative area. And I can use that to rewrite my limits of integration. Instead of from x to b, it's going to be the integral from b to x of f of x dx. And now look at what I have done here. This is an accumulation function. And this is another accumulation function. And I know that the values of these accumulation functions are my big F of x plus C1 and my big F of x plus C2. And hey, I've got some subtraction going on here. So the big F of x's are going to cancel each other out, leaving me with C1 minus C2. This looks really promising. We can see that we have the difference of two things, and that's all we really need. Now, f of x, generally speaking, we set that as the integral from 0 to x of f of x dx or f of t dt. I've been very lazy about my abuse of notation here, using x to mean two different things, but I think you've got it at this point. Sorry, I ran out of room there at the end of that, so let me try rewriting that on a new line. We know that big F of x we set up as the integral from 0 to x of f of x dx. So we can break that up. The integral from 0 to x of f of x dx is equal to the integral from 0 to a of f of x dx plus the integral from a to x of f of x dx. This first thing is big F of x. This thing is big F evaluated at a. And I'm going to leave this alone because that's the thing we're looking for. And so just rearranging here, if I want the integral from a to x of f of x dx, it's got to be f of x minus f of a. And I'm just going to say similarly, big F of x minus big F of b is equal to the integral from b to x of little f of x dx. So just regurgitating what I had a page ago, the integral from a to b of little f of x dx is the integral from a to x of little f of x dx minus the integral from b to x of little f of x dx. And now that we know what those constants are, we can plug them in. This is f of x minus big F of a minus big F of x minus big F of b. And if we simplify those, the big F of x's cancel out, the minus and the minus cancel each other out, and we get big F of b minus big F of a, which is exactly what we said we were going to get. And so if we have an integral, a definite integral, say the integral from 1 to 7 of 2x minus x cubed, I can look at this. I can look at 2x minus x cubed, and I can find the antiderivative of that. It's going to be x squared minus 1/4 x to the fourth, just using the power rule, plus c, but it turns out we don't need the plus c in this case because we're going to be subtracting these things, and so it's not going to make any difference. But we take that and we evaluate it at our endpoints. And this notation, sometimes you'll just see a vertical bar on the right. I like enclosing the whole thing in brackets because it helps me make sure that I don't lose something along the way. But we want to take this whole thing, we want to evaluate it at our endpoints. So we plug in and we evaluate this function at 7. So we get 7 squared minus 1/4 times 7 to the 4th power, minus, evaluate when x is 1. 1 squared minus 1/4 times 1 to the 4th power. All right, 7 squared is 49. 7 to the 4th power is 2,401. 1 squared is 1, minus a minus is plus, and so we end up with 48 minus 2,402 over 4, and I guess we can try to simplify that. Um, 2,402 over 4, they're both even, so it will become 1,201 over 2. 48 is 96 over 2, so adding all those together, you get 1,297 over 2. I guess that's better, I don't know. Depends on your perspective. Maybe having it as a decimal number would be a little bit better still. 648 and a half, it looks like my calculator tells me. All right, so we can evaluate definite integrals without having to think about the definition, without having to think about limits, without having to think about geometry. And that is definitely fundamental, right? That definitely deserves the title of fundamental theorem. Let's take a look at one more. The integral from pi over 6 to pi over 3 of 2 times the sine of x dx. As I think about this, I think about that 2. It's in front. I don't really like it there, so let's get it out of the way. And then the antiderivative of sine is the negative of cosine. So we're going to have negative of cosine of x, and we're going to evaluate that at our limit points, pi over 6, pi over 3. All right. Cosine of pi over 3 is 1/2. Cosine of pi over 6 is negative root 3. Well, cosine of pi over 6 is root 3 over 2, and then we have a negative in there. Make sure you don't lose the negative and the fact that we subtract because it is evaluating the limits of integration. So there's 2 negatives here, which makes it positive. So we've got 2 times square root of 3 minus 1 all over 2. The 2's cancel each other out, and we're left with square root of 3 minus 1. Great. So here's one I would like you to take a look at. The integral from 0 to pi of x squared minus the cosine of x. Take a couple of minutes, see what you can come up with on this one, and I'll see you in the next video.